Hello everyone, my name is Han, and today we're going to take a look at Halo 2. So Halo 2 is a fairly new operating system that ZkSnarks uses in their latest network upgrade, Orchard. There's some code, and there's a book here called a Halo 2 book. So we are going to try to make, we're going to make a circuit that is creating a zero knowledge proof for the usual stuff we always do. It's the same example that Vitalik uses to demonstrate ZkSnarks. So this guy. So basically that we know a solution. We know X that fulfills this condition. X cubed plus X plus 5 equals 35, and the answer is 3. So without showing the number 3, we want to prove that we know 3, and we are able to solve this equation. So it's not enough to know that this equation is solvable. We also want to prove that we actually know the solution, but we don't want to show that we don't want to give the solution. So this is the same stuff that I've been doing with other proving systems like Planck and Growth 16. This time we're going to use Halo 2. Alright, so for this we need a new project. So I'm going to go to my Rust directory and say I want a new project called Halo 2 test. Okay, that should be good enough. Then we open this project. Should be fast. Come on, Rust. What are you doing to me? Rust. Halo 2 test. Trust this guy. Here we go, and we obviously need the Halo 2 dependencies. So I need proofs, and I need this guy. Okay, and our main program will be this. Alright, so there's an example that we're going to be greatly inspired from. This is the example here. So let's work through this stuff. We work backwards, right? We work from the end, and the end is testing the circuit. So what we do is K is the size of the circuit. So it's essentially the size of it depends on the number of variables and the number of constraints you have. This whole thing, if you haven't followed the story, is basically turning first this stuff here into a set of equations, polynomial equations, and then these equations would have a certain degree, so that the degree kind of based on that value here. So they say 4 is good enough for our stuff, for their stuff. Which is, since the example is also very simple, I think it's going to be good for us too. So what we do want is we want to solve this guy, x cubed plus x plus 5, and so we only have one value, which is x. So we call it the fp from, and the value we want is we know it's 3. So let's say 3 is the solution. So we want to prove that we know this value 3. That's our secret value. There's a constant value, which is the 5 in the x cubed. Let's put it here. It's x cubed plus x plus 5 equals 35. So the 5 is the constant, and we are going to pretend that it's 35 changes. It's a public input. So if we want to solve this for a different value, we can use the same circuit, which is change this 35. So that's an input, but that's a public input. So constant will be copy from 5. Okay. And then we have the 35, which is the result. So our result is 35. Okay. And now we have a circuit. So let's circuit equal my circuit. And the guy has this constant. And it has x. And x is the sum x here. So exactly the same stuff. And now we do, so we have the public inputs, which is in our case the vector of result. And we want to instantiate the prover. So it goes with the mock prover. And we are running it on cake 4, the circuit that we have, our vector of public inputs. And if everything is happy, we should be able to unwrap it, though there will be no error. Then we assert, the same stuff, right? We assert that there is, if we verify our statement, then it's okay. That's the meaning of this stuff. So if you see, this is not going to compile because we don't have the circuit here is. We don't have it. So what we need, we say we should have inside. We know that we want to have the constant, which is FP. FP is field point. Just field, not field point. There are two fields, and it's there's FP and FQ, depending which curve. So FP is always for this one. Everything is going to be FP. Constant, and then the other one is x, so that guy is option of FP. The idea here is that when we create the proof, we're gonna pass the value x that we know is the solution, the secret, but when we verify, this guy will be known, so not a value that we know. Alright, so that's already a bit better. But now we know that we are missing the implementation for circuit. So that's not going to work like this. You see, just like that. We need to say that my circuit implements this interface. Implement circuit for my circuit. And that guy is imported. Okay. We're missing the implementation. So could create a dummy one. Alright. Okay, so floor planner, we know that we don't need a fancy one for this, so we're going to use a simple floor planner. The config is essentially the layout of our the wires and the columns that we need for our circuit. So that's going to be another class structure my config. Okay, there's something in there for sure. So my config sounds good. This one is okay. So let's say it's the most circuit will be equal to self default. Okay, so there you go, self default, which means that this guy self circuit has to implement default interface. So we can derive default from here, and then we have the configure and synthesize. Okay, so these are the two big guys we have to do. So what do they mean? The idea here is that when we have this this tutorial is very good, the Vitalik one. So what he says is that the equation, this equation x cubed plus x plus 5, is first turned into a circuit. This is not the first guy, I think. Maybe. Where do you do that? I think there's a. I hope that's from 0 to 0, something like that. One, this one. So there's also the tutorial or the videos that I have made. Anyway, the summary is that in order to execute this statement, you break it down to a series of smaller statements that only involve basic operations, and these operations are then executed by gates. So in our case, what we're going to do is we're going to evaluate this expression x cubed plus x plus 5 as a series like this. X, first we have x, we do x times x, then we do x, that gives us the next time x2, and we do x2 times x, which gives us x3, x cubed. Then we have x cubed plus x, that gives us x3, x plus 5, and then we do x cubed and 5, which is x3, x plus 5, and then we say that the last one, this one, should be equal to 35. And we don't have the luxury to make like if you have a chip, you won't have this operator. Obviously, you won't have this operator hard-coded, implemented directly in hardware, but you will certainly have multiplication and addition. And multiplication and additions are implemented as gates, as fundamental instructions. So if you have these two, then you can make a series of statements that gradually builds the results that you want, the 35. And all these intermediate values would be the values that you implicitly prove you know, because starting by 3, if you didn't have the knowledge of 3, you wouldn't be able to know x squared, x cubed plus x, and so on and so forth. So our goal here is to make a circuit that implements this logic out of gates that implements the primitive operations. All right, so our circuit then is this is the synthesized part, right? So we can say that let's implement the synthesized part first. It gives us an idea of what we expect. So our chip will have very basic operations where we can load the value of x into some. So this whole thing would be like a matrix of values. So first we have to load the. It's like if you were working with a GPU where you have the chip is separated from your CPU. First thing you would do is you take values from the outside. In this case, it's our secret and our constants, and we load it into the registers of our chip. Then we do operations on these registers, and at the end we test the value of one of the register. So that's the idea here. So first we grab the configuration. So let's assume that we already have. Let's assume that you have really built the chip. So maybe we need to do. Let's say let chip equal my chip. So there's another one we're missing. My chip. And my chip, and then we create a new one. And based on the config. So that means that guy already, we know that he should have implementation by chip and a function new that takes the config, and then returns self, and the guy will be my chip, and then you have a config inside. So this guy needs to have config, and this guy will be this guy. That, and you should config, right? This is put into this line, and then we start loading this stuff. So let's we only have one variable x, and that's the result of loading the chip load with the private value. So this is a function we have to implement as well, because our chip is custom. Okay. So that's a function we have to implement. So how to do the load private. Okay, so we have actually 3 functions or 4. we have to load private, we have to load the constant, we have to do multiplication, and we have to do addition. Right? So that's, maybe it's easier if we go from that. My chip would have, so we can define instructions, the interface for the chip, which are the instructions. And that's what they do here, I think, at the beginning. Maybe you can do that. Yeah. Alright, instructions. So let's say this is our ops, right? So it has type num, it's on the numeric type of each cell, and we have load private cell for sure. The layouter. Okay, so the idea also is that the very cool thing with Halo 2 is that we can reason in terms of smaller concepts that actually wiring the entire circuit. We can create smaller chips and then ask our circuit to use these chips at different places, and then there's an engine, a layouter engine, that's going to move these components around and make it so that we don't use as many constraints as we would. It's kind of like if you have a breadboard and then you want to place your components, but you want to reduce the space that they take. This is now done automatically by a computer. Okay, so that's why you have a layouter that's going to be given to us, but we have to ask this layouter to put stuff on for us. So layouter FP, and then X is our secret value, which is an option of FP, and it outputs the number. Okay, so I think that's right, an error. It has to be error. So I think this is the type of this function. Yeah. So we have one for private, we have one for the constant. So constant here, it cannot be option, right? Because it was options because there are two phases. One phase where we prove we have the value, and one phase where we verify. So we don't have the value. But for constant, the value is independent of the phase. It's known in the problem. In our case, it's the 5. So this is it's like that, and then we have the multiplication and the addition. So for doing, let's copy this guy again. Only the difference with multiplication is that we have two operands. So we have A and we have B. Okay, I think that's. We are already inside. Sorry, that's the difference. We don't have that. These guys are loading from the outside. So once we are inside the circuit, it's done. The numbers. We're actually using cells now. So it's num and num. Right. I think I have to do cell. Okay, and then we have also addition. Okay, so this is the trade compile. Clone is not implemented, so I need to have clone here. Let's do derive clone. Okay. Expected result found. Okay, these are not implemented. So let me put it as to do. Okay, that's also good. So it's just a trait. We want the chip, my chip, to implement that trait. So we're going to do that. Okay, this is this logic here. My chip implement the trait. Right? So let's say implement ops for my chip, and then we can say up. So this guy here is the number of FP. Okay. And now we just need what's going on. Oh, okay. There is something I Oh, it's assigned cell. Yes, this is that guy here. This guy is number. Okay, just say number then. I'm just gonna say assigned cell of FFV. Okay, and now load private. Okay, so load private is also going to use the layouter, and we're going to tell the layouter. I'm going to grab the config. Okay, maybe not. Layouter assign region. So we're going to use part of the chip here to do something. So this is going to give me just a closure. Gives me the name. And then I can use any name I want for debugging. Load private, and then assignment is sort of the region, and does something with it. So region. Okay, so we can do assign advice. Okay, assign advice. Annotation. Another big breaking message. Load private advice. Okay, private. This guy says that the role of that part of the chip, private value, private value, okay, private value, and then column. All right, so column is what columns our chip has. So we need what we need one column. These are basically the inputs of the component, so the pins basically of our chip. We need one for X, and yeah, so we're gonna want to lay out this stuff. Every time it's like two guys, right? So we need two advice columns, and yeah, we need the two advice columns. So let's see if that's enough. Probably not going to be enough, but we definitely need two advice columns. So they come from the config. Where's the config? My config. Okay, my config is here. So advice is column of type advice, and two of them. I don't know which one. Let's break this one. Okay, so column advice. You need to take the config. The cell config, but config has to follow the interface, not my chip. Just wondering if I have to declare this config accessor in a particular way. Okay, chip. My chip has to implement chip, right? Did I do it already? Yeah, I didn't do it yet, but they're probably gonna ask me to do it. Actually, I'm surprised they didn't. Okay, let me comment it out. Let's see what to do. Can copy this one. My chip. Because I haven't used my chip yet. Where is my chip usage? Build the circuit. Okay, anyways, they said that at one point it's gonna bite me in the butt. So definitely they say my chip has to implement interface chip. So let's do it. My chip, implement chip, FP for my chip. So if I do this, okay, So the config is my config. Loaded is nothing. There you go. So this has to return still the config. And this has to return nothing. Alright, so we have these two. So that means that here I can use that. Layouter had to be mutable. And I think this is it actually. Right, this is going to return the value I want. Oh, something's missing here. What do I need here? Column, right? Self.config of device, column 0. Right? And then offset 0. And the value that I'm loading is value. Okay, so EV is the value somewhere here. V. What do they need? Let's come over here. My config using debug. This my config also needs debug. My config. Where is it? Okay, here, debug. Okay. Expected result for an option. Okay, so that means that this guy has to be cast to a result. So it's okay or error, and the error is I think this error. Okay. Alright, that worked. Is it the same as I thought it did? Load private region, assign device, private input, exactly, then configure by 0, 0, okay, map number. Okay, seems like this guy was not necessary, otherwise he would have yelled at me. Okay. Okay, load constant. So really much the same. Really much the same. Name will be load constant. This is constant. Also loaded in space 0. I think the only difference is that the value has a different type. Oh no, assign advice from constant as a helper. Assign advice from constant. And now constant. And then I can put constant here. She is also the. There should be cast as a. Let's see. Yeah, but helper is taking care of us. Alright, so now we know how to load the private value, we know how to load the constant, we have to have the multiplication. So multiplication. So our gate would have basically one instruction, one constraint or two constraints. With one for multiplication and one for addition. And we select which one we use based on a column called the selector column. So if we do a multiplication, like here, right? If you do a multiplication, we are going to say that we're enabling the selector multiplication. Right, so let's do that. These two functions are going to be very similar. Layouter, also an assign region. This time it's multiplication. Multiple region. Okay. It's got also multiple here. Now, okay, so what do? We grab the config, forgot that. And then we do config, we do a region, sorry, assign device. So that should be the result of the multiplication. Actually, we don't have that yet. So that's a bit premature. So we have to enable the multiplication selector. So we don't have it yet. Devices. So we have device here. So we have SM should be a column of different. The selector or something. Selector. Okay, so in this case, selector. Okay, Okay, we have two of them, so I predict so we're gonna need a second one for add. Let's make it add as well. Okay, we continue from okay, so I have a problem with my recording. Selector, right? We need two selectors. The selector we'll see that later, but basically the selector will determine which condition we want, because some of the rows in our final statement will just don't have constraint. They will just be inputs, and okay, the layout at the end would be something like first we have x, then we put x, and we have 4 columns. So advanced column 1 would be A B, and sector multiplication and sector addition. Sum. Okay. So x, we put x and x, and we say we want a multiplication. Then the result will be in the next column, so it would be x squared. Then we put x again here, and we want another multiplication. So then at the end would be x3. Our chip will do that. Then we put the next here, but this time we say we want a sum, so something like that. And then our gate will do x3 plus x. Right. And then here we put 5, and then we want a sum again, and it would be x3 plus x plus 5, and then this is the final output. And we want this guy here, the final output, to be equal to 35. So each row of our if you want, you can consider that each row is incrementation of the program counter, and at each line we execute the same gate, which is our add multiplication gate, so our custom gate, and that gate will do either multiplication of A and B or the sum of A and B, depending on what we select here. So if we had 0, 0, then it would not be doing anything. So that's the general idea of our stuff. Okay, so we have two selectors, and here, right, our multiplication means that we are setting the multiplication guy to enabling this one, this region. So syntax-wise, I don't know. Where is this? It's not this guy. It's this guy. Right? So yeah, we have to borrow the multiplication, and there's offset 0. Okay. Then we copy the advice columns into here and here for A0. So A is a num, right? So A0 is actually the FP value inside, and we copy that. What's going on here? Why did it? Maybe I have to restart there. Good if I cannot. Is it? Yeah. So no. Okay, see that copy advice. What's going on here? Unknown field. Okay, so multiplication is not what I think. Okay. Okay. Self.none. Oh, he wrapped the scuff, right? And number. Oh yeah, Microsoft didn't run this. So for me, it's just A. Right, that's okay. A, copy advice, and then what's inside? Annotation. So that's gonna be left hand side. Right? And then next one is multiple region. Okay. Then the column is config advice 0. And then offset 0. Okay. Second one is B. B, we copy B to the right hand side, and it's advice 1. It's also offset 0. And then finally we do the product. So the product is so the thing is A can be known. So we have to do A value that gets the value or as an option, and then we do the and then we change the stuff together. That A will be now the real value, and then we do a B dot value, which is also an option, and then we can map this where we have this time B. It's very annoying actually the way it's written, but now we have A and B as we can do it this way. Yeah. Okay. Okay, no, maybe that's the option. Yeah, Versa has no like short way to write this. In functional languages, you would have the bind operator. Anyway, now we have the return, so we can do this guy exactly the same. Let's just do it here. So region, assign advice. So this is a product. Let's call it beta P. Beta P, and that's the value on outside on column 0. Yeah. But now offset 1 because we're talking about the next line, the next row, and we'll put V the same as here. Okay, and then we can say that's it. So same thing as this guy there, but we had to calculate V. And the add is the same thing, but instead of doing multiplication, we do add. So we call this one add, and then we call this one plus, and then we do a plus here, of course. Layouter has to be mutable as well. Okay, it's going to be here. Result must be used. Okay, question mark. Okay, so that was this part, and the last function we need is the constraint. So we need to make the constraint. Let's go. I could expose public. Okay, expose public. That's the one where the final value of our system, this guy here, is going to be brought back to and checked as equal to 35. So we need the layouter. We also need the value and then the position. The self num and the row size. Tell the same stuff. Let's go down here. Because I can close this guy. Drop the config, and then layouter is a constraint instance. So it's done as a cell, and then that guy is it should be equal to our config instance. So instances are public value. So we don't have this field. We don't have this field. So we need this field. That's instance. So it's a column of type instance. What's going on here? It's going to be result. Oh, no, it's because this guy is no value here. So we are good. If both public, this guy will not find no interface. Okay. So here we go. Let's combine. No. Not found in the scope. It's not instance. No, we have to import it. Maybe it's an instance. Let's go. Patterns are not allowed to function without all these. Okay. So what else we are missing? Okay, so missing the synthesize and the config. Okay. Synthesize. So we have the chip, and now, okay, so this is the part where we implement this logic over there. So we'll put it as a comment here, and then follow this. So now we can load our resources right here. Let x equal load private. We have the layouter. The namespace is so that we know if there's an error while loading x, where it was. Namespace, comma, and then we're loading x. Okay. We also load our constant if we want. Chip load constant. Layouter namespace constant, and then that is the answer constant. Okay, and then we do. Actually, I don't think it should be okay. What's wrong? This has to be mutable. Okay, so now we do x times x. So we do the first multiplication. X2 is chip multiplication. This namespace guy. So that's x2, and then we have x. I have to clone this guy. X and x clone. Okay. X3 is x2 and x. Let's go x3. Then x3 plus x. x3 plus x is x3 and x, but now it's add. And then x3 plus x plus 5 is x3 plus 5. So it's x3 plus x. And then here is this constant, which we don't need to clone. Okay. And then finally, we have to say that this is the same as the value was public. So namespace again. Expose result. And that guy is x3, x and 5. That's row 0. Okay, let's synthesize. Okay, my config. Alright, so we need this guy here. Right, so we have to do here. This is actually where we build a chip. Configure. So we have advice columns. We have 2 of them. Then meta advice column and meta advice column. Okay. We have one instance column, meta instance column, and we have one constant, which is meta fixed column. And our chip, my chip, is all these guys. Okay, so please don't wire. Alright, we didn't wire this configure. Okay, so I don't have this function yet. Configure the passing device instance and constant. Please create this function for me. Okay, this should be config. Generate. Oh no, can't do it. Okay, so my chip configure here. Fn advice is it's quite annoying. So this guy. Instance is this guy. And constant and not to pass. Not building this guy, so constant is not there. Right, and this should return self and to do. Okay. So there's no it's not self. It's config. This is matching here. So match config here. Okay, so configure is the most interesting one because it's where we define our gate. So far we have done everything. I mean, this stuff here, right, was the implementation of this set of equation of these steps. So the program itself, application integration. This stuff here was actually how the input wires and output wires are calculated if you have the right result. So this is how we do. We use Rust here, right? So this is calculated by Rust. So this has nothing to do yet with the proving system. So all this stuff is pretty much unrelated to Hello per se. But now is where we have the definition of our gate, because it's the meta. Okay, so we have to pass more stuff. Yeah, we have to pass meta as well. Because this is the only place where we are actually using the constraint system. So this is where the fun happens. This is meta. License constant. Well, actually we have to configure also the constant one. Column fixed. So we are telling the constraint system. We'll have to go. Stop. Alright, so the last part was what? The configure. The configure has the constraint system. So this is where the things will happen. We have meta advice. Okay, the advice columns are our witness columns, the stuff where we have our input values. Instance is the public value, and constant is the constant stuff. So what are we going to do first is to configure these guys properly. We have to say that advice. Okay, what is going on here? Meta enable constant. So constant is a constant, right? And then we say that there are that instance is equality, because we want the output to be equal to that value. Enable equality of instance, and then the true advice of for advice store meta enable. There are also equality for the device columns. Okay, and now we have our two selectors, M and S. So we have to create them. Selector S notification is meta selector, and then the second one is SAD, that is also a selector. And now our gate. We create a gate. Do we have a name, which is so it's a multiplication or add gate, and the constraint. So the constraint is a function, and that's just apply. What's going on here? It's actually just a name. Now this guy is what we want. Alright, so to the left, we want to implement this logic here. So the left hand side is picked up by killing the advice column, so create advice on advice 0, first column, and this is where we use the indication which row. So rotation current is the current row. Okay, the right hand side is S1, also on the current row, and the output, the result, is the advice column, so this one, on the next row, so next. Okay, and then we pick out two selectors, create selector on this selector here, and the same for this selector here. Okay, and the constraint is that okay, so if this guy is 1, then we have the left hand side multiplied by right hand side minus out. So this guy should be 0. So if this guy is 0, this guy doesn't matter, because then the product will be 0. And if this guy is not 0, which is 1, then this guy has to be 0. So our constraint is that guy has to be 0. Right, so this is for multiplication, and for add, it's the same one, but on the add one, and we want plus here. Alright, so there's a bunch of errors because the value has been used. We can use it once. So we have to clone this, and clone that. Okay, so that's our gate. It's pretty much the same as this one, logic here. And then we return our configuration. My config. Right, so my config, what is missing? Device we have, instance, multiplication advisory. So everything is here. So we remove it. So you need to do left. No, everything is done. Okay. So can we build? Okay. The tree bound hello. What's going on here? The tree hello advice is not available for indie. Okay, so that's the problem. This guy is a reference, and this should be passed by value. So star here. This function is for to pass constant. Okay. What's going on here? Okay, it's not good. SAD was never read. So if SAD was never read, that means something was not properly. That's multiplication. Why? Okay. This should be read in the here. Oh yeah, it's add here. Okay. Alright. So let's also format this doodle. This one is called here test. Gonna keep it rest to test. Okay, it's going on here. We didn't clone. Okay. So that one is saying that we don't need to clone it twice because we don't use x afterwards. So x cube. Okay, this one is not needed. No, it's needed. Yeah, we don't need to clone x2 because we don't need it afterwards. And x3 is the same. And then this one is the same. Okay. Okay, let's try again. We don't clone on x for x, we don't need that guy. Alright, so that's it. Alright, let's see if it works. We run. Okay, so if we run, this should be okay. Yeah, it worked. And if I don't put 3 but put 4, then it's gonna fail. Yeah, it's failed. So that means that knowing 3 is critical. Okay, what else can we do for this guy? So this is the testing circuit. Yeah, okay. Alright, do they have other examples? One cool thing is the visualization of the circuit. So I hope they have it somewhere. Why is it taking so long? What's going on with it? Examples. Circuit layout, maybe this one. Okay, and yeah, it's cool. So plotters. And then this one features thing. Okay, so use plotter prelude. Bitmap backend layout. Okay, this is probably this one. Why Alright, this guy. It's basically doing drawing. So let's keep this guy. And we want to see how our circuit looks like. this comes from it has to be under test or something. What's going on with GitHub? Come on. Plotters version optional true. Okay, so I don't really need this thing. Let's get this 3. But I want to have dev graphs. Dev graph. So hello proof version graph features dev graph. Then layout PNG. Alright, so we run this function. And use variable. Oh yeah, it's not using anymore. Okay, so this should give me test. Yeah, picture. Nothing really interesting actually. Okay, so it shows that I'm not using much of this stuff actually, just this part. 1, 2, 3, 4, 5, 6. Okay, these are our inputs. And then we have one multiplication. Let's see. It matches what we expect. Okay, what did we do? We did. This one is loading the private secret. One load the constant. Then we did a multiplication. It takes 2 rows, one multiplication, another multiplication, add, and then we calculate the result. So this is our this stuff here. And then on each step we use the chip. Alright, so okay, next time we look at something. I look at something a bit more complicated than this, but that's already. I think it's pretty cool. It's the same circuit again as the same statement that we had in the Vitalik example or many other examples. And okay, one thing we can do so is actually generate the real proof. Okay, so they have an example of that. Code implementation. Okay. Examples. Cost model. Okay. Circuit from ops. I don't know about that. Proof size. Okay, I don't know. That's not what I'm looking for. Alright, we'll finish here. And then next time we actually generate proof. We'll not use a mock prover, but the real prover. Maybe that could be interesting. Okay, this is a mock prover. Alright, that's it. Let's start with here. Kitchen, okay. And afterwards, what's that? instances. Okay, first of all, we have one circuit, one line here, and then instance. This should be the public variable. Where is it? Instance. Okay. So where's this guy? Where's don't need two. Where's RNG and transcript? Transcript is where's RNG? You need and public input was this guy, 35, and we build a product, the circuit with 3. So the only thing we don't have is this 3 here. Transcript is missing. Where's transcript? Click. What? Transcript. T. The product instance is identified internally, but where is this guy? T. Transcript, right? Probably. Yeah, zero idea what that means. Let's go and do the same as this guy. What I can see is that this is where the proof will end up. Then the proof is well, 1K. 1K to prove this. That's not small. Okay, these proofs are not small. This is cool. It's like how to verify multiple proofs at the same time. Okay, this is single one. Single verifier, transcript do the same dude. Verify proof. Okay, let's try that. So we take this code and we put it here. Give me single verifier, same parameter, back to the emitter, and then verifier. Okay, that should be okay. Okay, first of all, 2 cents, only 1 cent. And big inputs. Okay. Moved. Moved. What did he move? Move here. Try clone it again. Alright. And now we verify. Okay, verify. And let's see if we change this guy to, I don't know, 36, then the proof will not check. Let's see here. Yes, is 35. Let's see, now I want to click 36. So that should not verify. Fail. Okay, so at least that shows it works. Then leave verify here. And this. Okay, alright.